Look at this query on the screen. It asks the database to find one specific order hidden inside a massive table of 1 billion rows. When you run a search like this in a modern application, you usually get your answer back in about 2 milliseconds. This diagram shows exactly how the system pulls off that speed. To find your order, the database did not scan a billion rows. Instead, it used a structure called a B-tree, and to find your exact record, it only had to read exactly 4 chunks of data from your hard drive. Zooming in on one of those chunks, we can see the basic building block of the whole system. The database organizes everything into fixed-size rooms called 8 kilobyte pages. This size is intentional. It perfectly matches the physical sectors on your storage drive, meaning the computer can grab an entire page in a single clean motion. Notice how these upper pages do not contain any actual customer data. They only hold routing keys, essentially a directory of numbers that tell the database which page to check next. These compact routing pages provide a massive efficiency boost. By storing directions rather than the data itself, a single read allows the database to instantly ignore 99.9% of the other records in the table. This equation on screen explains how that elimination works. It calculates a concept called fan-out. If we take our 8 kilobyte page and divide it by the tiny size of a routing key, we find that a single page can hold about 583 directions to the level below it. When we follow those 583 branches down to a second level, each of those new pages also holds 583 keys. Multiply them together, and just 2 levels of this tree can organize over 340,000 rows of data. Expanding down to a third level, the tree can route us to almost 200 million records, and when we add a fourth level, the total capacity explodes to 115 billion rows. Thanks to this massive multiplication, almost no real-world database requires a tree deeper than 4 levels. Whether you are searching 10,000 rows or 100 billion, the maximum number of physical disk reads you need to find your target is capped at 4. Let's trace our original query through this structure. The search starts at the very top, at the root node. The database checks the routing keys, figures out which branch holds our target ID, and executes read number 1. Moving down to the next page, the database instantly ignores the rest of the tree, slicing away millions of irrelevant rows. It checks the directory again, giving us read number 2. At the third level down, the search space narrows to a handful of specific pages. One more quick comparison gives us read number 3. Finally, we land on a leaf node at the very bottom. This page holds the actual pointer, the exact coordinate on your hard drive where the full customer record lives. That is read number 4. With the exact physical location in hand, the database makes one final fetch to grab the complete row and ensure you have permission to view it. By treating the database like a highly organized map rather than a giant list, those 4 targeted hops bypass the need to ever scan the table itself. But what if you aren't looking for one specific order? This new query asks for every event that happened over an entire week. A single vertical drop down the tree cannot pull a range of rows at once. To solve this, the database descends exactly as before, but its goal is strictly to find the very first date in your range, January 1st, located in the leftmost qualifying leaf page. Here is how it grabs the rest of the week. These leaf pages are connected horizontally by a 2-way pathway called a doubly linked list. Once the database finds the starting date, it stops moving vertically and simply walks sideways from page to page until it hits January 7th. This horizontal walk lets the hardware read continuous blocks of data straight off the disk, turning a complex search into a simple linear scan. This structure is highly efficient for reading, but writing data requires careful management. In this diagram, a leaf node runs completely out of space. The database has to pause, allocate a new page, split the data in half, and send a new routing key up to the parent page above it. These page splits are usually rare, but they become a serious problem if you use sequential numbers, like a timestamp or a standard auto-incrementing ID for your primary index. Because timestamps only ever go up, every single new record is routed to the exact same page on the far right edge of the tree. If thousands of users are saving orders at once, you get a traffic jam. All those writes are piling up at the exact same location, forcing the database to lock the page and make everyone wait in line. Randomized IDs, like UUIDs, present that traffic jam by scattering new data across the entire base of the tree. However, this creates a trade-off. Because the data is no longer grouped together by time, the physical drive has to perform more work to jump between different locations during a search, losing the efficiency of those linear scans we saw earlier. You also have to be careful when building an index on multiple columns at once, like combining user ID and status. This works like a physical phone book, which is sorted by last name, then first name. If you only know a first name, the phone book sorting provides no help. Similarly, an index sorted by ID then status provides zero routing help for a query filtering only on status. Simply adding an index to your table does not guarantee a fast query. The speed only materializes when your query perfectly aligns with how the database routes data on the actual disk.